Alright, silly people, here's the situation. I bet y'all thought I was done doing Goldstein problems, but no, we're back with a vengeance on this one. Because this is a really cool diagram, first of all. And I swear to you, the colors are a lot nicer to look at on my tablet, where all the colors are nice and muted. But on the screen, it looks a little bit awful, but that's okay. But yeah, what we're doing is we're going to be sending a particle into a hard sphere of radius minus v0, um, or its radius a, and then the potential of the sphere is minus v naught. And then it's going to scatter a couple of times within the sphere. So that's what's happening on the intersection between v1 and v2, is it's scattering off of the surface of the sphere with angle beta, and then it's going to scatter again as it's exiting the sphere, and then that is scattering with an angle, or an absolute angle theta with respect to the incident particle ray. So yeah, the first thing that you are asked to do is you have to basically kind of prove Snell's law for this, and that is that you're trying to prove that there is a relationship between the sine of angle alpha with n sine angle beta, right? Um, and that you actually end up doing via conservation of angular momentum, because you know that initial angular momentum has to be equal to the final angular momentum, and angular momentum is given by rho cross or r cross p. So this is going to be r cross p initial equals r cross p final. R in both cases is a, because it's just the radius of the sphere and it's in the direction of r hat. So a r hat cross, and then p initial is m times v initial, so mv1, and it's in the direction of, I'll just say v1 hat. And then on the right hand side, it's a r hat cross mv2 v2 hat. So we've got amv1 r hat cross v1 hat equals amv2 r hat cross v2 hat. Notice we can go ahead and cancel out a's and m's. But also, r cross v1 hat is the sine of the angle between them, and the sine of the angle between r hat and v1 we already know to be alpha. So this is going to be v1 sine alpha on this side. And on the right side, we've got v2, and then the angle between r and v2, this guy and this guy, is beta. So it's v2 sine beta, which means very simply that sine alpha equals v2 over v1 sine beta, and you can also write it as n if you really wanted to. But that's not the form that n that Goldstein actually wanted it in. He wanted it in terms of like energies and potential energies. And so to do that, you say, okay, we know what the energy is before and after the first scatter. Before the first scatter, the energy is, it's mv1 squared over 2, all kinetic energy. After the first scatter, it's going to be the same energy, so E, and then, but now it's being split up into mv2 squared over 2 and minus v naught, right? That's just the total energy in there, and the total energies have to be conserved. So we can use both of these guys, rearranging both of them for v2 and v1 respectively. Looks like we got E plus v naught times 2 over m, and then square rooted equals v2. And then before the scatter, we got 2e over m square root equals v1. So we can combine those expressions here. So v2 over v1 will be big ol' square root here, 2e plus v naught over m, and then divided by another big ol' square root, 2e over m. The 2's cancel out, the m's cancel out, so you do get e plus v naught over e, which is, what he was asking for. So I think that takes care of the first bit. I think the very next step of the problem is actually to find the differential cross-section. And to do that, we are going to need the scattering angle theta, which I've already labeled, but I haven't written what it is. So it's this angle between the green dashed line, which is the axis of the incident particle, and then v3, which is the axis of the particle's final state. So what we're going to do is we're going to notice that via similar triangles, this theta, or not even similar triangles, this theta all the way out here is this angle here, theta. So what can we do with that? Well, we know that this angle is 180 minus theta, right? And so this angle here is alpha minus beta, and this total angle here is actually theta, given the fact, or it's actually alpha, given the fact that these are similar triangles. That is alpha as well. So then this little angle here, this angle here is also alpha minus beta. So 180 minus theta plus 2 times alpha minus beta should be equal to 180. The 180's cancel out, so you get theta equals 2 times alpha minus beta. Geometry, folks. So let's zoom back out now, so I remember how. There we go. And write that here. Theta is 2 times alpha minus beta. Okay, so that's pretty cool. But also for the scattering differential cross-section, the formula is sigma of theta equals s over sine theta ds d theta. So we also need s, which I've already labeled. It's the impact parameter. And also, due to the fact that the triangle on the outside is similar to the one on the inside, I'll say that this line here between the center of the circle to to the v1 vector is also s, right? So I mean, at that point, the hypotenuse of that triangle is a, so then it's going to be s equals a sine alpha. Okay, let me write that down. S equals a sine alpha. What you do here is you put alpha in terms of theta, because it has to be s of theta, right? And alpha and beta are related to theta by theta equals 2 times alpha minus beta. So alpha equals theta minus 2 beta over 2. So this is a sine of theta over 2 minus beta. Then you do a trig identity. You use the one where it splits up sine of x plus sine of y, and also this should be plus beta, just noticed. But yeah, it's sine theta over 2 cosine beta plus cosine of theta over 2 sine beta, right? Okay. Well, we can relate sine beta back to sine alpha from here. So it's a sine theta over 2 cosine beta plus, and now this is 1 over n. So let me write this in big stuff here. 1 over n cosine theta over 2 sine alpha. And then alpha you put in terms of theta again. Theta over 2. Or actually, no, you put sine alpha in terms of the scattering angle, the impact parameter. God, all these classical mechanics terms are really fun. That's s times a now. Okay, so let's pull the factor of s that's in here to the left-hand side, so we get s times 1 minus 1 over n times cosine of theta over 2. And on the right-hand side, we're going to be left with a sine theta over 2 cosine beta. And in fact, let's just multiply both sides of the equation by n, shall we? So if we have s n minus cosine theta over 2 equals n a sine theta over 2 cosine beta. And then square both sides. And this is more so to try and simplify the right-hand side than to do the left. So I'm not even going to expand that yet. So it's going to be n squared a squared sine squared theta over 2 cosine squared beta. And then cosine squared beta is 1 minus sine squared beta. So it's can be related back to sine alpha again. So it's 1 minus, what was it? It'll be 1 over n squared sine squared alpha. 1 over n squared sine squared alpha. Glorious. Now we can move this, or actually now relate sine squared alpha back to the impact parameter, which is a sine alpha. So I swear this algebra is going somewhere. It's going to be really cool. 1 minus sine squared alpha is going to give you s squared over a squared n squared. And then it's just, yeah, that's it. So then now I'm going to move the stuff which depend on s squared over to the left-hand side again. So it's s squared all times, in parentheses, n minus cosine theta over 2 squared plus now just sine squared theta over 2, right? And then on the right-hand side, looks like we have just a n squared a squared sine squared theta over 2, right? Pretty cool, pretty cool. Now let's expand the square on the left-hand side because we have to now, but then immediately move it to the denominator of the right-hand side. So it's n squared a squared sine squared theta over 2 all over n squared minus 2 cosine theta over 2 plus cosine squared theta over 2 plus sine squared theta over 2. And guys, cosine squared plus sine squared equals 1. So that will greatly simplify our expression, but not that much, not by that much. Theta over 2 plus 1, right? Take the square root of this equation, and now you have an equation for s. It's a n sine theta over 2 over square root n minus 2 cosine. And there really should be an n here. I just noticed that. I'm just going to stick it in post haste. Plus 1. Yeah, okay. Fantastic. Let's do now the scattering differential cross section, which is S sine theta ds d theta. So I guess we better do the derivative of this with respect to theta first. And this is going to be gross. I want to do the quotient rule. Quotient rule is a pretty controversial choice, I know. And also I'm going to go ahead and just say it's a n out here, multiplying all of it, and I'm going to make it a big fraction. So I'm going to put the a n like here. And then it's going to be times the fraction. I don't know why I'm putting it there, actually. It sucks there. A n. Denominator times the derivative of the numerator. So actually it's just root n minus 2n cosine theta over 2 plus 1 times cosine theta over 2 all over 2. That's why I wanted to make this a big fraction, because this, I'm going to scoot it up a little bit and stick it all above a 2, plus, or actually now minus the numerator times the derivative of the denominator, so it's sine theta over 2 times, and then I'm going to put the stuff dependent on the 2 on cosine theta over 2 up on the top. So it's minus 2. It's going to be 2n sine theta over 2 divided by 2. So just n sine theta over 2. Yeah, that's it. And then all divided by 2 times n minus 2n cosine theta over 2 plus 1, that factor of 2 coming from the fact that we're doing a chain rule derivative. And it's all divided by the denominator squared, so n minus 2n cosine theta over 2 plus 1. Okay. The fractions up top, let's make sure that they have the same denominator, yeah? And we'll do that by multiplying the cosine theta over 2 stuff with the square root stuff on the bottom. So it's n minus 2n, and I'm going to put this in braces, cosine theta over 2 plus 1 times cosine theta over 2 minus n sine squared theta over 2 all over n minus 2n cosine theta over 2 plus 1 to the 3 halves. Isn't that fun? And then let's also try to multiply some of this stuff through, because we're going to have a cosine theta over 2 times n minus 2n cosine squared theta over 2 plus cosine theta over 2. I'm going to go ahead and expand sine squared of theta over 2 as 1 minus cosine squared theta over 2. And all divided by the junk on the bottom. I kind of made that line too high, but it's okay. The denominator is not that big of a deal. And so we have n times cosine squared theta over 2 minus n plus n cosine squared theta over 2. So keeping track of all the stuff dependent on n, it's just minus n cosine squared theta over 2 plus cosine theta over 2 minus n now. And this can be factored. And if you looked at the problem, you'll probably already know the form of that. You can probably guess it because this is like we're almost at the being done with the proof. But that is going to end up being, let me look at the book here. Yeah, it's cosine theta over 2 minus n times 1 minus n cosine theta over 2. That only makes sense if I did the square right, which I didn't, because this is n squared, this is n squared, this is n squared, and this is n squared. So this is n squared, and this is n squared, and this is n squared, and this is n squared. Yeah. So this is n squared, and this is n squared. And I think I fixed all the n squared stuff. Let me make sure. Because it's going to be plus n squared cosine theta over 2 checks out. Plus cosine theta over 2, yeah, minus n, yep, and then minus n cosine squared theta, yeah, okay, I fixed it. I'm so sorry about that, gang. I miss a little square on occasion. But okay. That is done. And we'll write it like over n squared minus 2n cosine theta over 2 plus n to the 3 halves. Okay. Now, finally, we can do the differential cross section. Because it'll be s over sine theta, and s way the hell back up here was an sine theta over 2. So we're doing a squared n squared sine theta over 2, all divided by 2 sine theta, and then in the brackets, the square root on this term is going to move into this little guy here to give, in brackets, cosine theta over 2 minus n, 1 minus n cosine theta over 2, all over, in parentheses, n squared minus 2n cosine theta over 2 plus 1 squared. And I think that's even. Are we done? No, we're not quite done. He puts it in terms of a cosine on the bottom. So now let's just work on the trig functions out front. So sine of 2 theta goes like 2 times sine of theta over 2 times cosine theta over 2. So this is 4 sine theta over 2 cosine theta over 2. The sines cancel out, so you get 1 over 4 cosine theta over 2. That was like the least painful part of this whole problem. So we're getting a squared n squared sine, and then now we have over 4 cosine theta over 2 on bottom, and then the wacky stuff in the bracket that I hope I don't have to look at again, which I probably will. I'm actually doing this for a quantum field theory assignment, funnily enough, right now. Boom, done. That's the form that the book got it in as well. So now the final thing that it's asking for is to do the total cross-section for the thing, which is, to be the integral, or it's 2 pi times the integral from 0 to the maximum scattering angle times the differential cross-section sine theta d theta. So, funnily enough, this has a different form because sigma of theta is s over sine theta, and then this is times ds d theta, and then this is the Jacobian, so sine theta d theta. The sine thetas cancel out, the d thetas cancel out, so it's kind of like just a integral over s of it's just an SDS from 0 to theta max, which doesn't mean just plug in theta max, right? Because this is going to be now pi, and then in brackets here, already evaluating at the endpoints, s squared of theta max minus s squared at 0. What is the maximum impact parameter? Well, going all the way back up to our nice little drawing, the maximum impact parameter possible is if the particle just grazes the top of the sphere. So I'll do it in big magenta, but this is the maximum impact parameter if it's all the way up here. Which means it's just equal to A. So going back down here, we'll have that. Now this problem is really long. That S of theta max is just equal to A. So we have pi of A squared, S of 0. Well, if you plug 0 into our impact parameter equation, here you'll have sine of 0 up top, which is 0. So that term doesn't contribute either. So you just get pi a squared. That wasn't horrible.